Yeah, hi everybody. This is, I'm sure, going to go rough. It's the first one we're doing, but we'll see how it goes. Keep in mind, if we're not in school on Tuesday, then I'm going to do another of these for Tuesday that will be due on Wednesday. So what you want to do is fill out your notes according to what I say here. And we're going to get through most of the chapter. So variables that describe a gas, there's four variables. Pressure, which we measure in kilopascals. Volume, which we measure in liters. Temperature, which we measure in Kelvin. And moles, which is given the always exciting MOL. So not much of an abbreviation there. Factors affecting gas pressure, the amount of gas. By adding gas, you increase the number of gas particles. That should make sense. This increases the number of collisions, which increases the gas pressure. So here is a diagram of a cylinder. And in the cylinder, we're going to give it a little bit of a gauge. And the gauge shows a needle. And we have 5 particles. And the particles are moving around at some kind of velocity. And what we're going to do is then, so let's say 5 particles with a pressure of 100 kilopascals. We're going to draw the same container. Remember, tomorrow you have to show me the notes. It's going to have more particles in, so it's going to have more pressure. So this time we're going to put 10 particles in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 particles. What should happen to the pressure? Well, since we double the number of particles, and we'll have these things zipping along in some kind of straight line motion, we should double the pressure. So instead of 100 kilopascals, this should have a pressure of 200 kilopascals. So the more pressure, the more particles, the higher the pressure. Number 2, volume. Pressure can also be raised in a container by reducing its volume. The more the gas is compressed, the greater the pressure. As you push down on a container, you increase the pressure inside. If you have double the pressure, you will have half of the volume. If you take half of the pressure, you will double the volume. So if the pressure on a gas is halved, it's less, then its volume must have doubled. If the pressure on a gas is doubled, then its volume must have halved. Remember, you can always stop the video if you start getting tired of listening to me and start it up again later. So here we have a cylinder. In it, we have some kind of a piston, which is pushing down with a force of 100 kPas. Sorry about the interruption. It's 3:05. With a volume equal to 1.0 liters. So what we're going to do is we're going to double the pressure so that the pressure is 200 kPas. What will the new volume be? Since you're doubling the pressure, you will get half of the volume. And the volume will equal 0.5 liters. All of this stuff we can talk about in class if you don't get it. So number 3, temperature. The kinetic energy increases as the temperature of the particles increases. The higher the temperature, the more kinetic energy. The faster moving particles hit the walls with more energy, which increases the pressure. Doubling the Kelvin temperature doubles the pressure. Taking half of the Kelvin temperature, will half the pressure. If the pressure on a gas is doubled, the Kelvin temperature must have doubled. If the pressure on the gas is halved, then the Kelvin temperature must have been halved. So here we have another cylinder. It's at 300 Kelvin. It has a pressure of 100 kilopascals. There are 6 particles in the container. Let's make it 7. 6, 7. And over here, we have a container. It still has 7 particles in it. We haven't changed number of particles. But now, we double the temperature to 600 Kelvin. What happened to the pressure? What is the new pressure? So let's draw a little candle here to show we increased the heat, and the pressure should double to 200 kPas. We're going to try now and get through some of the gas laws. Gas laws. Pressure-volume relationship, which is called Boyle's law. We've already discussed this, so there's nothing new. Consider the effect of pressure on volume. When pressure goes up, volume goes down. When the pressure goes down, the volume goes up. So it's an inverse relationship. Mathematically, we say pressure times volume at one set of conditions is equal to pressure times volume at a separate set of conditions. So if we were to graph this, there is a pressure of 1 atmosphere. It has a volume of 10 liters. So let's double the pressure to 2. It has a volume of 5. Let's double that pressure to 4. It has a volume of 2.5. And we see we get this downward sloping graph. You must know that the relationship, when graphed, of pressure versus volume is a downward moving graph. The second relationship or law is Charles' law, and it relates temperature. We've already done it. When temperature increases, the volume increases. When the temperature decreases, the volume decreases. This is a direct relationship. In a direct relationship, the formula is this. Volume divided by temperature will equal volume divided by temperature. Here on the Kelvin scale, if we are at a temperature of 150 Kelvin, our volume is 300. If we double it to 300 Kelvin, our volume jumps up to 600. So this time we have a straight line because of the direct relationship. When a direct relationship is graphed, the result is a straight line. Another important feature is that if we extrapolate all the lines backwards, we extrapolate to 0 volume at the same point, 0 Kelvin. Thus, this is the temperature which would theoretically be 0. You can't have a negative volume, and it's the lowest possible temperature that a body can attain. The third relationship is pressure and temperature, but we already talked about it. When the temperature increases, the pressure increases. When the temperature decreases, the pressure decreases. So the law states that the pressure of the gas is directly proportional to its Kelvin temperature. Since it's another direct relationship, we have this equation. We end up with the same kind of graph. So if you double the pressure, it's because you doubled the Kelvin temperature. We're almost done. This leads us to what is called the combined gas law. In the combined gas law, we don't have to remember 3 different equations. They're all combined into one. And it's P1V1 over T1 equals P2V2 over T2. What if we hold temperature constant? If we hold temperature constant, it's not part of the equation because it cancels out, and we're left with Boyle's law. We can cross off the temperatures. But if the pressure is held constant, if we cross off the pressures from the original combined gas law, then we're left with Charles' law. What if the volume is held constant? Then we can get rid of the volume term, and we're left with Guy-Lussac's law. P1 over T1 equals P2 over T2. If none of the variables are constant, then we're left with the combined gas law. So that was our first lecture. I hope it went okay for you. Tomorrow in class, we will, you can ask me questions about any of the laws, but we're going to work on a worksheet so that I can see what you're doing in class, and then if you finish that, then we'll have time for you to work on your homework. But again, if school is canceled tomorrow, then I'm going to have another recording for you to do tomorrow at home. So have a great night, and we'll see you tomorrow, hopefully in school.